Hi, I'm Brian Thornberry. I'm going to show you how to create and edit footprints on KiCad 5.1. In this video, I will demonstrate how to create a footprint for the TP4056 lithium-ion battery charger. In the end, it will look something like this. I will walk you through calculating pad positions from datasheet dimensions and using the footprint editor. If there's enough demand, I may create a tutorial series on the entire circuit. The project I have open is a lithium-ion battery power bank I'm creating to power my Raspberry Pi. It allows you to charge the battery and power the Raspberry Pi at the same time, and unplug the USB without resetting the Pi, features you won't find in most power banks at the store. It will use a single 18650 lithium-ion cell scavenged from old power banks. In it, I'm using two cheap Chinese components, the TP4056 lithium-ion battery charger with protection circuit and the MT3608 boost converter. The TP4056 manages the charging logic for the lithium-ion cell, while the MT3608 boosts the output from 3.7 volts to 5 volts so I can power the Raspberry Pi. The TP4056 comes in several variations, as you can see here. I will create a footprint for this variation, which includes the battery protection circuit. I ordered these from Amazon.com in the KES pack shown here. Before we begin, it's important to understand lithium-ion batteries may be dangerous to work with, and I recommend doing research before building a circuit like this one. Use the information in this video at your own risk and see our disclaimer in the description below. Whenever you set about creating a footprint, I recommend creating a drawing like the one I've created here. Usually I would just do this on paper, but for the sake of this video, I created a PDF. To understand what is going on with all these numbers, first we need to take a look at how the coordinate system in the footprint editor works. The axis of the footprint editor is aligned as you see here, where the positive x-axis goes to the right and the positive y-axis goes to the bottom. The center of the footprint editor is 0, 0. It's very important to understand that the x and y position of any component placed in the footprint editor is relative to its center. For that reason, you can see that the arrows and gray numbers here represent the distances between the center of pads or the length of boundary lines. In almost every datasheet you will find a figure similar to this, listing out the distances between the center of the pads and showing the overall size of the package. It's your job to convert these distances into coordinates of each component that we can use in the footprint editor. In this case, you can see I've done that with the numbers in red. How you do this is entirely up to you. In this drawing, you can see that I've placed the origin, 0, 0, in the center of the pads and calculated the position of each pad and boundary line endpoint relative to this. I could have placed the origin at the top left and ended up with completely different positions, but a still perfectly valid footprint. Each of the numbers represents an XY position measured in millimeters. I always work in millimeters when creating footprints because most datasheets I've come across use millimeters. Some engineers prefer to work in inches, and ultimately, this is up to you. You can easily convert between units as you prefer. Now, let's open up the footprint editor and get started. Every footprint needs to be placed inside a library, as you can see to the left here. To start, we'll create a personal library and then create a footprint inside it. Press File, New Library, navigate to your KiCad directory or wherever you like to save the footprint library. Give it a name. I'll call mine A Personal. I like to put the A in front so it comes up first in the list, but you can call yours whatever you like. Press Save. If you'd only like to use these footprints in this project, go ahead and add the library to the project table. I'm going to add mine to the global table so I can use it in other projects. Right-click on your library on the left and press New Footprint. Give it a name. I'm going to call mine TP4056. Now we can start making the footprint. Remember to like and subscribe if this video is useful for you. To start, let's change the grid size down to 10 mils. Make sure your units are set to millimeters. Because we already laid the groundwork with our drawing, creating the footprint will be straightforward. To start, let's zoom out and move these two texts over the way. Click and drag to select them and press M and go ahead and move them up to the left, good and out of the way. We'll need them later, but we don't need them for now. Now let's place our first pad. Go ahead and click the Add Pad button here and set it anywhere up in the top left. Don't worry too much about the position for now. press Escape, and then select the pad and press E. This opens up the Edit screen, where we can edit its properties. If this were a pin for a through-hole component, we would use the default through-hole type. I'm going to solder these components directly to the board like a surface mount component though. So let's change the pad type to SMD and the shape to rectangular. Let's set the position of the pad matching the position of the plus pad on our drawing, negative 11.45x and negative 7.1 Y. Now we set the pad size to 2.8 millimeters width and 2.8 millimeters height. We'll keep the default options on the right, ensuring that the front copper layer f.cu is selected, and press OK. Now we can see our pad is in the correct position, but our text is in the way. We didn't move it quite far enough. Go ahead and just move those again. We'll come back to those later. In this case, we've left the pad number to 1, but it's very important that the pad numbers on the footprint match the pad numbers from the schematic. You can see how I've mapped out the pad numbers on the schematic symbol, and I'll make sure the pad numbers on the footprint match. Let's place the remaining pads in their rough areas. You can see the Add Pad tool automatically copies the properties of the previously placed pad like size and type, and increments a number for you. It looks like I've made a mistake. The 4 pad should be on the bottom. To delete a pad, put the cursor over the pad and press delete. Now we'll place our pads with the correct numbering. Now let's put each of these in the correct position. Now that we've got all the pins in the right place, let's place the board outline on the silkscreen layer. Select the Add Graphic Line button, then click once roughly along the top left and again roughly along the top right. Don't worry too much about where this is at, we're going to fix it in a moment. Press Escape to stop drawing, switch back to your cursor tool, zoom in and select the line and press E. Set the endpoints of the line as they appear in our drawing. Negative 13.05 starting X and negative 8.9 starting Y, 15.35 ending X, and negative 8.9 ending Y. Go ahead and press OK. Now we can progress one line at a time. Zooming in to select the endpoint of the previously placed line, and then roughly placing it, coming back and editing the properties as I showed before. On this second line, all we need to do is set the endpoint X to negative 13.05 and the endpoint Y to 8.9. Now that the board outline is complete, I like to place a small circle near pad 1 outside of the board outline. To do this, select the Add Graphic Circle button, click once near pad 1, and just move your mouse a little bit to create a small circle. We're going to move this so that it's a little bit closer to the board outline. The final step, let's move our 2 text pieces into a reasonable place. Ref star star is a special value that will be replaced with a component designator like U1 or R1 depending on the schematic. Don't worry about it for now, but we'll place it at the top. TP4056 won't actually show up on the final PCB, but we'll go ahead and place it at the bottom. Now you could polish this up and create additional text like we have here, out plus, B plus, all labeling the different pins and where the USB would be. But ultimately, that's just for yourself, since that's going to be covered up underneath the soldered on component anyways. So let's leave it how it is, press File, Save, and now we're finished. Like and subscribe if you found this video useful.